Welcome, we're going to be looking at Little Man Computer. This is the Craig and Dave version. There are several Little Man computers you can find on the web. They all operate roughly in the same way, but we found this one to be the neatest and more up to date. So over on the left hand side you've got the assembly code version. Now assembly code are the instructions that Little Man Computer can use. A much smaller set of instructions than you would have on a real CPU, which would have hundreds of different operation codes that you can use. But you can simply find some Little Man Computer code on the web and just tap it in here, or use one of the programs that you've already seen. This is a very simple Little Man Computer program that inputs a number, stores the number in a memory location, identified by the label number down here, so it's address 6, inputs a second number, and then adds to that number whatever's stored in the memory address, and then outputs the result of the add. So essentially it inputs two numbers, adds them together. Now, as we've said before, this may seem to be a very, very simple program, but everything your phone, everything your computer does really amounts to just loading things from memory, doing some calculation, and then throwing the data back to memory. Do that several million times a second, and you've got yourself a computer game running. Down at the bottom, you can load in some code that's been previously saved, save your current program, and you can assemble, that is, check the instructions that you've typed in and get them loaded into memory. So over here on the memory area, you've got 100 memory locations, each of which is capable of storing 3 digits. The first digit corresponds to the instruction code. The second and third digits either identify what the instruction is, or they're a memory address. You'll see how this works later. In the central area, we have the CPU itself. Top left, the control unit with a nice little crib sheet of all the different Little Man Computer instructions and their corresponding first digit. And when the control unit splits the instruction up into its opcode and the data, you can see that here. Just below that, the arithmetic logic unit, that's where calculations obviously will take place. And we've got a nice little pie chart here to indicate whether we're in the fetch, decode, or execute part of the cycle. On the right-hand side of the CPU, we've got the registers. So we've got the program counter that indicates which instruction is current, a memory address register, so whenever we're sending something to memory, that'll be filled up and the data will go down the address bus. The control bus, which sends either an instruction to say read or an instruction to say write. The memory data register, which obviously either receives data from memory or holds the data when data's being stored. And if the data being received as an instruction, it will then be popped into the current instruction register. This isn't actually in the GCSE specification. It's kind of useful to know that there is a record of the current instruction, and some GCSE specifications, and the one we use at A-level, require knowledge of the current instruction register, so it's there anyway. And then of course the accumulator, which in my opinion really should be over here in the ALU, but it's there anyway, close by. At the bottom, a little box where you'll be asked to input data and a box where output will be displayed. And finally, over on the bottom right, a button to reset the whole thing back to the beginning, a run button, and then you can run a single part of the cycle, so just a fetch part and a decode part and so on, or an entire single cycle. Up here in settings, you've got an opportunity to change various things, turn the animations off, but you might want to just do what I'm doing, which is to just slightly speed up the speed. The default speed is a little bit slow. So let's press run and see what happens. So the first thing that happens obviously is the program counter value goes via the memory address register through to memory, and the read instruction causes that instruction to be fetched, and it arrives eventually in the memory data register, gets copied to the current instruction register, and then through to the control unit where it's decoded. Now 901 represents an input instruction, so I'm going to put in the number 55, and the 55 then is going to get stored in the accumulator. We're then ready for instruction 1 to now be executed, so 1 goes through to memory, a read instruction from the control bus from the control unit, and the 306 from that address is read in, drops into the current instruction register, and then goes through to the control unit. Now 306 is a store operation, so we're going to store the current ALU in memory. So 6 goes through to memory, a write instruction is then sent to memory, and the 55 in the memory data register is then sent through to memory, and sure enough, address 6 will get the value 55. On to instruction 2, 901. It's another input instruction. So I'm going to speed this a little bit up. Okay, so I'm going to target the value 90. So I'm going to actually add 35 in to this value now. So 35 now goes into the accumulator. You notice the 55 gets overwritten. Don't worry, we've got it stored here. So we then go and fetch the instruction in location 3, which is 106. And so we read that instruction through. Now, if we look at the little crib here, 106 is actually the add instruction. So 06 means we're going to add to the accumulator whatever's stored in address 6, which happens to be our 55. So to execute this instruction, the address we want to read the data from is sent through to memory. Control bus will send a read instruction, and the 55 will be retrieved. So it's not an instruction, it's the actual data 55 gets read and put into the memory data register. So it won't overwrite the current instruction. That then goes to the ALU. The ALU brings in the accumulator, adds those together, and then stores the result, the 90, in the accumulator. So the final instruction is 902. This is going to be an output instruction. So when the 902 is fetched and executed, it's simply going to send the value in the accumulator through to the output. So here it is arriving in the control unit, gets decoded, and that simply sends the accumulator through to the output. Our 90 has now been displayed. The final cycle is a pretty boring one, really. We read the instruction 000, which is actually our halt instruction. Just simply tells the computer, tells the CPU to stop executing instructions. So that's Little Man Computer, a nice little simulator to visually show the fetch, decode, execute cycle and help you learn the process. There are loads of Little Man Computer assembly instructions that you can copy off the web. You can obviously try out the ones that we've seen in this unit. And the important thing, like anything in computing, is to play.